Good morning, mathematicians. Thank you for joining me today as we go out and we're going to do some fishing in South Carolina. It's a beautiful May morning, so we're going to go out and see if we can catch some fish and do some math along the way. While I was out fishing, I ran into a couple related rates problems that I wanted to share with you. As we do related rates problems, there's a whole process involved, and instead of writing it all down here, what I'm going to do is I'll provide a link to the written version of this, and we'll just run through quickly what we're going to do. The first step is that we're going to, well, this is an applied problem, so we're going to have to read the problem as it's given to us, or as it's related to us in this video, and we're going to have to determine what's being said and what's being given. After that, we're going to look at anything that's changing, and we're going to assign variables. So as we assign variables, we decide what we're going to call things, and we write it down so that we can keep track of it as we go. Once we know what's changing, then because this is a related rates problem, we're going to have rates to deal with, which means we're going to have derivatives to deal with. So you write down any derivatives that we have, and we include any information that was given to us in the problem. Once we have our information from the problem written into a mathematical model, which is what we have now, we have to now find an equation relating to rates. So anything that was given to us that we want to find or was given to us, we find an equation that involves those. And then after that, we're going to implicitly differentiate. Then we're going to plug in the information as given to us to solve for what we're looking for, so that in the end we can find the solution to the original problem. Now once we have the model solved, we go back and we say, well, what was the situation we're in? And so we're going to give our answer in terms of the original question. For this related rates problem, what we're going to have is, you'll notice that my wife Paula is sitting on a fishing boat, and she casts her fishing line out into the lake. It's a nice calm lake, so as the fishing lure hits the lake, it creates a ripple. That ripple is circular, and as it expands out, we notice that it's expanding at 3 inches per second. And what we want to know is, what is the rate at which the area of the ripple is increasing? Now, as our first step, we need to read through the problem again. So as we look at that, I would suggest pulling that one up so you can look that over. But we'll notice that the first couple sentences, we're talking about casting fishing line on a calm lake and throwing a lure out. And really that's just setting the place of the example. And so it's not giving us anything that we're going to need for our model, but it's giving us information that we'll need to give the answer to the ending question. Now the first thing that we run into that is really helpful for our model is that we notice that the ripple is a circle. And so what we're going to do is we're going to start off and we're just going to draw in a circle around that ripple so that we remember that it is a circle. The next sentence tells us that if the radius of the ripple is increasing at 3 inches per second, so what we have to do there is we notice that that's giving us more information. So what's going to happen is that the radius is getting bigger, and it's getting bigger at a rate of 3 inches per second. So in order to keep track of that, what we're going to do is we're going to draw a line going out showing that the radius is getting bigger. We're going to put down 3 inches per second so we know it's getting bigger by 3 inches per second. As that sentence continues, we get how fast is the area increasing if the radius is 24 inches. Well, this is really telling us two things. The first thing is that it's asking how fast is the area of the ripple increasing. So that's telling us what we're supposed to find. That is, what is the rate of change of area with respect to time at this given point in time. And so what we're going to do is we're going to draw an arrow again. This looks similar to the radius, so we have to remember that we're trying to show that the area is getting bigger. And so we want to know what rate is the area getting bigger. And so we're going to put a question mark there so that we know that that's what we're trying to find. The next thing we notice is that it tells us that the radius is currently 24 inches. We know that the radius is getting bigger by 3 inches per second, so it's not going to stay there. But right now it's 24 inches. So we're going to draw in our radius, and we're going to note that as 24 inches. Now that we have a picture representing the situation that we're given, and we have all the information written down that was given to us and what was asked of us, what we need to do is we need to start assigning variables so we can create a model. Now we notice that, yes, the radius is increasing by 3 inches per second. That means the radius is changing. Because the radius is changing, we have to assign it a variable. Now, as opposed to always using x and y's as we've done in the past, what I want to do is I want to pick a variable that makes sense to me. something that later on I'm going to remember when I refer back and I see that and say, okay, well, I know what that means. In this case, I would suggest picking R for radius because R for radius makes sense. So we're going to denote R as a radius. The next thing we see that's changing is the area because we want to know how fast the area is changing. So we're going to denote the area as, well, I like to use capital A for area because it makes sense to me. Note that if you guys want to use different variables, you're welcome to. I'm just picking the ones that make the most sense to me. Now the last thing that's changing is time because over time things are changing. So we're going to let T denote time. And so we're going to have the variables A, R, and T. Now I would point out here that there is plenty of other things changing in the situation. You could talk about temperature or water depth or anything else you want to talk about. And in fact, a lot of times there are other variables that you may want to look at or may not want to look at. But what we're going to do in the beginning is we're only going to deal with variables that say, okay, these are the things that are given to us. Hopefully those are enough variables that we don't have to make up more. So because radius was explicitly mentioned, because area was explicitly mentioned, we include those. And as a point, because we're dealing with related rates, it says how is it changing over time. Time becomes a variable we're going to need, and so we're going to leave it as those three variables. Now that we have our variables, we have to find any rates that are given in the problem. And so the first thing we notice is that the radius is increasing. In fact, the radius is increasing by 3 inches per second. So what that means is that because the radius is increasing, there's something about the derivative of the radius. So the dr, d something, is equal to 3 inches per second. Now the something we find by looking at it's inches per second. Seconds are measurement of our time. So what we're going to get is dr dt is 3 and then inches per second. Now as we're converting this to model, I'm going to leave the units off. So I'm going to say that dr dt is 3. Now the one thing I do want to be careful of is that is my derivative positive or is it negative? And in this case what we want to know is a positive derivative means my function's getting bigger. Negative derivative means my function's getting smaller. So in this case, is my radius getting bigger or smaller? And when we know that the radius is increasing, the ripple is getting bigger, so therefore dr dt is a positive 3. Now the next thing we look at is we want to know the rate of change of area with respect to time. So that is, we want to know dA dt. So the derivative of area, dA, with respect to time is dA dt. That's what we're looking for, so I'm going to write that in as my question mark. Now that we've found our variables and our rates, we have to find a function relating the different variables and rates that we have. In this case, what we notice is that, well, the ripple is a circle. So because it's a circle, we can look at the area of a circle is pi r squared. So we get the equation A equals pi r squared. Notice that both area and radius are in there, so we have an equation relating these two, and so we can use this to find what we're looking for. Alright, now that we've got in our equation A equals pi r squared relating area and radius, what we need to do is we need to implicitly differentiate the equation so that we can find dA dt. Now because we're looking for dA dt, we're going to take the derivative of both sides with respect to time. So what we're going to get is d dt of the left-hand side is d dt of the right-hand side. Now what we have here is dt of A is just dA dt. We don't know what A is, so we can't actually find this derivative, so we're just going to leave it implicitly as dA dt, and that's going to be equal to. Now, if we take the derivative of the right-hand side, what we have to remember is that r is actually a function of time. Because r is a function of time, we actually have a chain rule here. Now, the outside function is going to be pi times I squared. So the derivative of the outside is going to be 2 pi times I. Now, the inside function is r. Well, since we don't know what r is, the best we can say is that di dt is just dr dt. So we get dr dt. Now, because I introduced that letter I, I'm just going to get rid of it. And so we're going to find that dA dt is 2 pi r dr dt. Now, if you want more practice with this, go back and look over the implicit differentiation video, and hopefully you can get some more help with this. But now that we've gotten out the implicit differentiation and we've found the derivative, what we need to do is, well, right now, what is dA dt? In order to find that, we're going to plug in what we know to find what we don't. In particular, we don't know dA dt right now because that's what we're looking for, so we're going to leave that alone. But we get 2 pi. Currently, the radius is 24, so instead of r, we're going to plug in 24. And currently, the r dt is 3. So what we get is that dA dt is 2 pi times 24 times 3, or it is 144 pi, which is approximately 455.2. And so what we've done here is we had our equation, we implicitly differentiated it, we plugged in what we knew to find what we were looking for, and we have actually solved our model in finding that dA dt is 455.2. Now, if we just write down dA dt as 455.2, it doesn't really answer our original question about the radius or the area of the circle, and so what we need to go back and do is figure out what we were actually trying to find. So that is, we have a solution to the model, but we need to give an answer to the original question. And so what the original question was asking is, at what rate is the area of the ripple increasing? And we found dA dt was 455.2. So what we would say is that the area is increasing because the derivative is positive. It is, the area is getting bigger by 455.2, and then we have to give some units on there too. And so what we have is, well, radius was in inches, and remember that area was pi r squared. Since pi is unitless, r is in inches, so r squared is inches squared, area ends up being inches squared. Now, time is in seconds, so dA dt is inches squared per second, so we end up with is, the area is increasing by 452.2 inches squared per second. Now that seems like a mouthful, so it may be worth taking some time and thinking, okay, well, how would I explain this to somebody else? If I had to do this, if they asked me this question, I would try to do this in a colloquial way. So I would say, well, the ripple is getting bigger by 455.2 square inches per second. Thank you for joining me today. I hope you enjoyed these applications. If you did, make sure to like this and let me know. If there are any other situations that you'd like me to look at, also let me know in the comments below, and I'll be happy to try to do a video for those. While you're at it, make sure to subscribe to the channel so that you are updated on all the new stuff that comes out.